Alright, so I'm going to talk today about the effect of coordinating the coordinating ligand and oxidation state on octaethylporphyrin carbonyls. And my name is Adrian. So let's first talk a little bit about octaethylporphyrin carbonyls. Iron porphyrins, usually in animals or in life, are known as hemes, and they are found in a lot of proteins, such as hemoglobin, myoglobin, cytochrome P450s, that sort of thing. Even in photosynthesis, there's a porphyrin ring that acts as the electron charge carrier, and they're found all across life, and we want to understand how these proteins all work. So some of these proteins are really big and complex, so we try and use model compounds or model complexes to understand the interactions between the porphyrin and, say, a ligand that's attached to it. And these ligands usually come from the proteins. One of these that is used quite ubiquitously is octaethylporphyrin, which is a tetrapyrrole ring with ethyl groups at all, or occupying all of the pyrrole positions. And it's a pretty good model for heme because of the electronics are very similar to heme in heme B, which is the typical heme that is found in these proteins. And in this study, I used spin polarized DUFT because, as you can see on the side here, I had some that weren't singlets. I had some doublets as well. And just for the total energy calculations, you can see that by adding the tyrosine to it, it had the greatest effect on the electronics out of any of the other substituents. So over here, we can see the energy in EV as calculated by DFT, where the phenol is ligated to the iron porphyrin with the carbonyl on the opposite side. Carbonyl is just there to make sure that it's A, low spin, because it's a very strong field ligand, and B, just a fixed ligand there so that the iron is in an octahedral electronic geometry. It's easier to calculate that way. So, phenol, and then if you change it to phenoxide here, so take away the proton, you have a formal negative charge on the oxygen, you can see that it's basically identical in electron or total electron energy. And then here, if you add a tyrosine, it changes it quite dramatically. And we're actually going to see why that happens in a few slides here, where I show the Homo of this tyrosine complex. But the geometry changes radically when we add the tyrosine to it. But over here, I took the phenol complex and I changed the oxidation state between 0 and +3. And the reason I did that is just to look at some maybe intermediates that would happen during some catalysis, or if this is a non-typical example of a carbonyl. Usually carbonyls bind to the ferrous iron state, but they do have some affinity for ferric, and these other states can be accessed through enzymatic activity. So if you're looking over these, I mean, there's only a little over 15 EV difference, where the difference between these two here, it's on the order of 70 or 60 or so. So that there's a big difference from that tyrosine. Looking at the absorbance spectra, so this is an absorbance spectra of nickel octaethylporphyrin. Nickel octaethylporphyrin, as you can see here, it's very easy to use because nickel only makes 4 coordinate bonds, and so it's just structure, nothing special going on about it. It can't get axial ligands or anything, so it's just really stable. And looking at it, you have this one really large band here, right around 400. This one is actually right at 392, and then you have 2 other bands here out in the 500 range. And this is a very typical heme spectrum that we see throughout, or porphyrin spectrum, that you see throughout even in proteins, out of proteins, in aqueous solution, in organic solution, it's very similar. Sometimes these change a little bit in intensity. Sometimes you get a charge transfer band out there. It just depends on what's going on. But it's very similar. But what was computed was not that. So you can see here, it should be something around 400 and something around 500 or so. But right here around 400, there's not much going on for absorbance intensity. And the reason is it's not, the heme, or the porphyrin ring interacts very interestingly with itself. And so your HOMO and your HOMO -1 actually both have a pi to pi star transition, where they both go to this EG pi star orbital in basically all porphyrins. And these two orbitals are so close in energy that they end up actually interacting with each other. The excited states interact with each other, and you end up getting this very similar thing. I don't think DFT fully understands that, what's going on there, because it's a very unique example compared to something like, just a simple CO2 absorbance spectrum, something like that. And then, as you can see here, overall, these three all look fairly similar, except for the tyrosine here has two bands where the phenol and the phenoxide both have basically just one band. There's a little bit of a side band here in the phenol, but it's not that big. And then over here, as you change the number of electrons in the system, and you get a formal charge from -2 to +1, as you can see here, basically what happens is everything shifts to the blue. So it's, but the one interesting part here is the formerly iron 1. It basically has no absorbance spectrum going on. It's very odd, but interesting nonetheless. All right. So just looking at the HOMO orbitals here, or HOMO geometries and orbitals, you can see here that we have the octaethyl porphyrin. We're looking right down the porphyrin plane. Right down here we have our phenol. You can see a little hydrogen here. And as you can see, most of the HOMO intensity or electron affinity is in this, right around this iron metal, and it looks very much like a D-based orbital with the 4 lobes. So as you can see here, it's fairly clear what's going on. There's a little bit here on the ligands as well, and a little bit out here on the ring, but it's basically all centered on the metal, which we can see here is very similar when we have the phenoxide. So you can see here that that proton is gone, so we have the phenoxide. There's a little bit more centered on this oxygen here than compared to before, but overall, it's pretty much all based on the metal. One thing of note here is you can see here the ring isn't as flat in this model. It has a little bit of a ripple in it, which is an interesting thing to look at, because in some proteins it does have that same different ripples in it, or different tilts and bends, and that needs to be explored further in our protein-based research. So this might be a good way of looking at what is going on in those systems. And here's where things get really funky. So when I put the tyrosine on, the tyrosine fell off. And so we can see here that most of the electron density is on this tyrosine ligand. So you can see it's coming out here. Here's the carbonyl side. Here's the amino side of the amino acid. And then here's where it should be ligating to the metal. So what I'm thinking happened is there was just too much weight or too much mass, reduced mass, that the oxygen bond wasn't strong enough to hold it together. And it does make sense. In proteins, it's not just that one oxygen bond that's holding it on. It's a whole bunch of interactions all the way around the ring that's holding it together. So it does have some merit. So with that, I'm going to give you some conclusions. First one is you want to use swell ligands. Obviously, the tyrosine fell off. It was pi stacking with the ring. Obviously, that's not what we wanted to look at. We wanted to look at what happens when we have ligands on there. So that's why the tyrosine ligand had such a large effect. And what we need to do is we need to use smaller ligands without the whole amino acid backbone on there. Otherwise, they won't give us results that we're looking for. So it seems to be a fairly effective way. There's a whole bunch of papers out there on DFT with these porphyrin rings where they are looking at different ligands, different substituents, that sort of thing, and they have used it to draw correlations to proteins. It doesn't seem to be very effective for generation of absorbance spectra, but I know I've read several papers where they have generated vibrational spectra, and they match fairly nicely with published experimental results. So there's one thing that we can use, but the absorbance spectra don't seem to be as useful, or obviously I did it incorrectly. Overall, the spin polarized unrestricted DFT does a fairly good job of calculating for iron porphyrins. With that, any questions?
Okay, thank you, Seth.